Hello all. Today we will be looking into signal detection in the presence of Awgn. So this is actually the continuation of the earlier lecture on signal space concept and the Gram-Schmidt orthogonalization procedure. So in this lecture we will see how those concepts of signal space can be applied in a digital communication system to do the signal detection in presence of Awgn noise. So we'll start with the communication system model. Then we will do a quick review of the signal space concepts that we have already done earlier. Then we will look into the signal space representation of Awgn noise. Then we will study about how a continuous Awgn channel can be converted to a vector channel. Then we will move on to signal detection. Then we will characterize it mathematically, both the signal, noise, everything. Then we will study about there are two rules for detection. One is called MAP, that is maximum a posteriori probability rule, and ML rule, that is a more common maximum likelihood rule. Then we will study about the correlation receiver, that is the optimum receiver in presence of Awgn. And lastly, we will analyze how the probability of error can be found out. So this is our system model. You have a transmitter. So a message source generates a message M. So assume that we have a total of capital M messages that needs to be transmitted. So these messages are transmitted using the waveforms, that is finite energy waveforms, SI of t. So the waveforms are represented as Sk of t when with k varies from 1 to m. Then you have an additive channel. So there is always noise represented as N of t, and this noise is, so you know, the noise is modeled as additive, white and Gaussian. So it is called Awgn noise. So this noise gets added up. So the receiver receives the input x of t, which is actually the sum of s of t and sk of t and n of t. The goal of the receiver is to detect which one of the capital M message signal was transmitted. So that is the goal. So how it is done? So we will use signal space concept that we have studied earlier, and we will convert these signals to vectors. So that is the idea, or that is a simplification that we use here to design an optimum receiver. An optimum receiver is one which results in the least probability of detection error. So we'll do a small review of the signal space concept. So it says that a finite energy signal Sk of t can be represented as a linear combination of capital N basis functions. So these basis functions forms an orthogonal basis set. So these basis functions are represented as phi j of t, where j varies from 1 to n. There are capital N basis functions. So the whole idea is, so we have already seen that the receiver x of t is sum of sk of t and n of t. So here what you have to understand is that the signal sk of t is deterministic. So we know a priori which all messages are mapped to this sk of t. So actually we have capital M messages. So each message will be mapped to one finite energy signal sk of t. So sk of t is deterministic, and we know that n of t is random, or n of t is probabilistic. So that means that the received signal x of t is also random. So our idea will be to model this received signal x of t as a random process. So this random process x of t is equal to capital N of t plus sk of t, and we already know n of t is zero mean, capital N of t is zero mean, additive, white, Gaussian noise. And we have already seen that using Gram-Schmidt orthogonalization process, this finite set sk of t can be represented as a point in a capital n dimensional signal space. So I can write sk of t is equal to sigma j equal to 1 to capital N skj into phi j of t, where this coefficient skj is the projection of our original signal sk of t at each of the basis functions phi j of t. So I can write skj is equal to integral sk of t into phi j of t. This is the same equation as before. Now the problem here is this Gram-Schmidt process is valid only for deterministic signals. So it is invalid for a random process. So we can't find or we can't represent a random process using an n-dimensional signal space, or we can represent a random process as a point in n-dimensional signal space. The maximum we can do is we can expand random process x of t as as a point in an infinite dimensional space, represented as x of t is equal to sigma j equal to 1 to infinity capital Xj phi j of t, where capital Xj are the coefficients, and this convergence is in the mean square sense. So this mean square sense implies the energy of this signal x is 0. So that is E of, actually energy of the signal and its energy of the difference between signal and its approximation is 0. So that means E of integral mod x of t minus sigma j equal to 1 to infinity xj phi j of t the whole square dt equal to 0. This is a moment is 0. So you can observe that here the random process is modeled as, so it can't be modeled as a finite dimensional space, it is modeled as a point in an infinite dimensional space, and that too the convergence is in mean square sense. So under quite general condition, a set phi j of t can be found out. So, and it is called as the KL expansion of the random process. So details are out of scope for our syllabus. And you can see that this x of t can be represented as some coefficient into phi of t, and each coefficient xj is a random variable. Now, using this concept, we will try to model Awgn as, or we will try to find out the signal space representation of Awgn. So consider the Whiteson stationary noise process n of t, which is modeled as a zero mean Awgn. So E of n of t is 0. So that is obvious because this is zero mean. And the autocorrelation function Rn of tau is, since this is a Whiteson stationary process, the autocorrelation depends only on the time difference. So we have already seen it. So Rn of tau is n naught by 2 into delta of tau, where delta of tau is the impulse function. So this autocorrelation, since it is white, so autocorrelation function is an impulse at the origin, and we already know since it is white, its power vector density will be constant, or it extends from 0 to infinity. Now let us model n of t as sigma j equal to 1 to infinity nj into phi j of t, and where nj is the coefficient, that is the projection of n of t on phi j of t. So here all the integrals will be taken from 0 to t. So that is our interval of that is our observation interval. So each finite energy signal, sk of t, it extends from, or it exists only from 0 to capital T. So it is finite duration also, sk of t. So we are considering only the duration 0 to t, and this capital T is actually, it is also the pulse duration. So each message will be represented as a pulse of duration capital T. Now E of nj equal to, so you can see that so this each nj will be a random variable, as we studied before. So we are trying to model this Awgn using the signal space, or we are trying to find the signal space representation of Awgn. So each nj is a random variable. Now we will try to find the mean of nj. So E of nj, you can see that it is E of integral 0 to t n of t phi j of t, and you can see you can use the property that the mean is 0, the mean of the random process is 0, and you will get it as, so therefore the expected value for the mean of nj is also 0. Now we will find the covariance of nk and nj. It is two coefficients nk and nj. So covariance is E of nk nj minus E of nk into E of nj. So the second time is 0 because E of nk and E of nj is 0. So it is E of nk nj. So we will substitute for nk and nj, and we will arrange the integral and the expectation. So you will get it like double integral E of n of t n of l phi k of t phi j of l dt dl. So E of n of t n of l is actually the autocorrelation. So that is n naught by 2 into delta of t minus l. So since it is Whiteson stationary, it depends only on the difference of the time, that is delta of t minus l. Then phi k of t into phi j of l. So we know that it is, so we have already studied it. It is actually orthonormal basis functions. So its inner product is 0 when k not equal to j, and when k equal to j, it is 1. So we can write the covariance nk nj as the function as given. Covariance of nk nj equal to n naught by 2 when k equal to j, and 0 when k not equal to j. So covariance between two random variables is 0. So that means that the random variables nk and nj are uncorrelated. So this capital N of t is a Gaussian process, and this using nk and nj, we are writing the Gaussian process as a linear combination of some basis functions. So since it is linear, we can get each of this nk and nj as Gaussian random variables, and since nk and nj are Gaussian random variables and they are uncorrelated, they are also independent. So that is a property of this Gaussian random variables. So if two Gaussian random variables are uncorrelated, they are also independent. So that implies each of the coefficients nk, nj, etc. are independent and uncorrelated of each other. Now we will consider our normal basis function set phi j of t sigma j equal to 1 to n. So we will use this basis. So we have seen that the random process requires infinite dimension to represent. So now we will use this basis as with the approximate extension to represent noise n of t. So n of t, what we will do is we will write n of t as n cap of t and n1 of t, where this n cap of t is the projection of the noise n of t in the n dimensional signal space, capital N dimensional signal space spanned by phi j of t. So we can write n cap of t as sigma j equal to 1 to n j into phi j of t. So this represents a part of our original signal n of t. So we have already seen that this n of t can be represented at least in mean square sense with infinite dimensions. So out of that, the part n cap of t represents the component in capital N dimensions, and the remaining is represented as n1 of t. So this nj is actually the projection of n of t in the each of phi j of t. Now we can write n1 of t as n of t minus n cap of t. That is straightforward. And we already know that the random process, the received signal random process x of t is sk of t plus n of t. So we substitute for sk of t and n of t. So we'll get this expression sigma j equal to 1 to n skj phi j of t. So this two combinedly represent n of t. So this is n cap of t. That's the n dimensional projection of the noise, and n1 of t is the remaining noise. So from there I can write x of t is equal to sigma skj plus nj phi j of t plus n1 of t. Now what we will do is we will write, or we will define a coefficient called xj as the sum of skj and nj. So we are substituting for that. So sk of t, so skj is actually the inner product between sk of t and phi j of t, and nj is inner product between n of t and phi j of t. So this xj is actually the sum of, so this represents inner product between sk of t, phi j of t, n of t and phi j of t. So that is inner product sk of t plus n of t phi j of t. So that gives a very interesting result, like xj is actually, this sk of t plus n of t is x of t. So xj is inner product between xj and phi j, x of t and phi j of t, or we get like the coefficient xj is actually the projection of x of t on phi j of t, where phi j of t is our n dimensional or capital N basis function which represents a n dimensional signal space. So we are substituting back to our original expression. X of t is, so we started from here, x of t is sk of t plus n of t, n of t is n cap of t plus n1 of t. So this 2 adds to, so this term and this term, so this 2 adds to sigma j equal to x cap of t, or sigma j equal to 1 to n xj phi j of t, and the remaining is n1 of t. So the received signal x of t is the sum of projection of x of t on phi j of t, where j varies from 1 to n, and an extra noise term n1 of t. Now we want to analyze whether this extra noise term n1 of t is relevant for our design of the optimal receiver. So we'll see. So we know that the noise process n of t is independent of signal sk of t. So both are independent. Noise is the property of the channel and sk of t is a deterministic signal. Therefore n1 of t being a part of capital N of t also will be independent of sk of t. So that's obvious. So there is no information about transmitted signal on capital N1 of t. Now, secondly, we need to observe where N1 of t and n cap of t does it have any correlation? So, this n of t is a Gaussian process. This n cap of t is a linear combination of the projection of n of t. So, that will also be a Gaussian process. So, therefore, n1 of t equal to n of t, capital N of t minus n cap of t also will be a Gaussian process. So, we are considering a time t and finding the covariance between nj and this n1 of t actually is a random process, but when we are considering at a particular time, then it becomes a random variable, or we are sampling at that particular instant. Now we are finding the covariance between the coefficient nj and n1 of t. So it is e of nj n1 of t minus e of nj into e of n1 of t. So it is e of nj n1 of t. We have already proved that e of nj is 0. So it is e of nj, and now we are substituting n of t minus n cap of t in place of n1 of t. So this n1 of t is n of t minus n cap of t, then expanding. Then we are writing the expression for nj. Nj is the projection of n of t on the space spanned by phi j of t's, and also e of nj and n cap of t is sigma L equal to 1 to n nl phi L of t, and we have already done. So rearranging this e of n of t n of s phi j of s, e of nj nl phi L of t. So this term is actually the autocorrelation function. So it is n naught by 2 delta of t minus s phi j of ds, and this we have already proved. This has a value only when j and l are equal, and it is n naught by 2. So L equal to j. So this we have already done. Covariance of nj and nl we have done before. So it is n naught by 2 into, this has a value only when j equal to l. So substituting j for l here. So n naught by 2 into phi j of t. So that implies it is 0. So this gives a very important result, like this. We have proved that n1 of t and nj are uncorrelated. So since they are both Gaussian, they are independent also. So that means n1 of t is uncorrelated with all the nj's, and therefore n1 of t should be uncorrelated in, n1 of t is uncorrelated and independent with all the nj's, and therefore it should be independent of n cap of t also. So we have proved two things. N1 of t doesn't have any relation with our transmitted signal, and also n1 of t is independent of n cap of t. That is, n cap of t is a projection of our noise in our signal space, the n-dimensional signal space. So this gives a very nice framework for developing our optimal receiver. So this n1 of t doesn't have any relevance, and therefore it can be neglected. This n1 of t doesn't depend on, n1 of t is independent of our signal sk of t, as well as n1 of t is independent of the noise projection n cap of t. So using this too, we will do a continuous Awgn detection. Okay. So these are the conventions used. Our received signal x of t, so it is reduced to x cap of t. So x cap of t is actually the projection of x of t on the n-dimensional n-dimensional signal space spanned by phi j of t. So we have already seen. So this x cap of t can be represented as vector x, which is equal to x1, x2, etc. xn. This is an n tuple, capital N tuple. So this vector represents our received signal. Then our transmitted signal sk of t. So it can be represented this. We have using some Gram-Schmidt normalization procedure. Sk of t can be represented as sk equal to sk1, sk2, skn, where skj is this. And n of t is our original noise. So we have seen that this original noise has two parts. So one part is the projection of noise on our n-dimensional signal space, and another part is n1 of t, and we have seen that n1 of t is irrelevant. So we are concerned only with n cap of t. So this n cap of t is thus becomes a point in the n-dimensional space. So it is represented as vector n equal to n1, n2, nn, where the coefficient nj is the inner product between n of t and phi j of t, or it is the projection of n of t on the signal space. So x cap of t contains the desired signal wave and the projection of the channel noise on the n-dimensional signal space spanned by phi j of t. So here it is clear that for the design of an optimal detector, the continuous Awgn channel of the form x of t equal to sk of t plus n of t. So this is a continuous channel. We are dealing with the continuous signals or the continuous random. So x of t and n of t are continuous random processes. So it is converted to an equivalent n-dimensional vector channel. X of t is converted to vector x, sk of t is converted to a vector sk, and n of t is converted to n. So all these vectors are n dimension as given here. So this is how a continuous Awgn channel is converted to a vector channel.